Okay. First, let me finish the discussion of free fermions, and then we'll try to look into interacting systems. For free fermions, I had mentioned last time that there is this space LA of n, local anti-symmetric matrices with a gap, and somehow the parameters like the locality radius and the gap are gone, and we have extracted the persistent homotopy type of those spaces with parameters. And there are maps alpha and beta that make LA into an omega spectrum. And this is a completely abstract statement. It only requires some general properties of local matrices, and we want to calculate that spectrum. And that spectrum happens to be the KO spectrum shifted by -2. But how do we see that? We need to somehow relate LAN and LAN plus 1 without making loops. And this is done using symmetries, namely Clifford symmetries. In addition to local matrices in n dimensions, one can consider local matrices in n dimensions with Clifford symmetries. And let me explain what that is. We consider the Clifford algebra. Clifford, maybe I'll use low indices, P and Q. It's a real Clifford algebra with generators E1 through EP plus Q, such that the first P generators square to 1. And the remaining generators square to -1. And these generators must anti-commute to make a Clifford algebra. And we consider matrices that anti-commute with those Clifford generators. For example, let C be a matrix, not necessarily local and not necessarily anti-symmetric, and we require that C times EJ equals minus EJ times C. And for example, let's consider the case of symmetric matrices and one positive generator. How does such a matrix look like? We can write the generator explicitly. It's E1, basically the Pauli matrix acting in a two-dimensional Hilbert space, tensor identity, acting on some other space. And then C can be written as a block matrix. This is also a block matrix. It's identity 0, 0, minus. And C has 4 blocks. And in order to anti-commute with this matrix, it must have 0 here and 0 there, and something in those blocks. And since C is symmetric, we can put a matrix Q here and Q transpose there. This is the general form of such a matrix that anti-commutes. And if we also require that C squares to 1, and remember that we talk about gapped matrices. Gapped matrices have C squared close to 1, not 0 and not very large. And this is equivalent to saying that Q transpose is the same as Q transpose Q, and it's identical. Symmetric matrices with one Clifford symmetry are equivalent to orthogonal matrices. And symmetric matrices with 2 Clifford symmetries, if we add E1 is before. Then C equals 0, 0. Now let me call this Q A.
You're missing a minus when you want, right?
Yeah, thank you. It's minus I. Let me just rename Q as A, and the anti-commutation with E2 means that A transpose must be equal to minus A. So now it's anti-symmetric. And in general, there is a formula, anti-symmetric matrices with P positive and Q negative generators are the same as, or the spaces mapped isomorphically to symmetric matrices. With Q plus 2 positive and P negative generators. In the previous calculation, we took P and Q equal to 0, and we got 2, 0. So C is a member A is a member of this. And C is a member of
Explain again what you mean by symmetric 2-0. Is it the symmetric matrix tensor with
No, symmetric to 0 means it anti-commutes with 2 Clifford generators. This was the previous calculation. We considered C of this form, and we required that this holds for all J. And J can be 1 or 2.
C is an operator on the representation.
Yeah, C is an operator acting on a representation of the Clifford algebra. Yeah. And we assumed a particular form of this representation. The generators have a specific form. So yeah.
These Clifford generators, they are data that you have to specify the matrix representation of them.
Yeah, we have to specify. However, we assume that we can enlarge spaces, and if we enlarge spaces in a suitable way, we can always write those Clifford generators in this particular form. Because in general, we can imagine. Anyway, you can make this assumption about those generators in a suitable basis. Now, we can apply this to local matrices. Anti-symmetric matrices with P and Q Clifford generators are the same as symmetric matrices with Q plus 2 and P Clifford generators. And now I want to split this map A into a product of two maps mu and nu. So we have L A E Q. I assume that P is greater than 0. Then we L A plus 1 P minus 1 Q. And L and this should be alpha. And there is an inverse map beta. I forgot to mention, with Clifford algebras, there is both periodicity. So this thing depends on E minus Q mod A. And this is a purely algebraic fact. One can map representations of Clifford algebras in a certain way, and I already did some of those mappings. Okay, how do we define mu? We have P Clifford generators there and P minus 1 Clifford generators there. Let's think about the first positive Clifford generator, E1. And in this case, let me assume that this E1 is represented by that matrix, like E2 in the previous discussion. And an anti-symmetric matrix A that anti-commutes with this Clifford generator has the form like A0. Oh, maybe I'll just say B minus B P minus C. This is a general form. This is a general form of a matrix that anti-commutes with this matrix. And using this matrix, we'll construct another matrix on a chain, because we make assume n equal to 0 for simplicity, but here n is 1. And this matrix on a chain will be called mu of A, and mu of A is the sum of 3 terms. The last term is like a discrete derivative. It has this metric structure, and it's tensor with some number A. The choice of this number is not important. We can assume it's 1. It's just for generality. So this is a new metric. So you can think that the original system consists of 2 sides like this, like the Majorana chain, but each little circle now may have multiple Majorana modes. In the Majorana chain, it was just 1. And we have this 0-dimensional template, and we repeat it periodically and make a one-dimensional system.
One of the dots is the B and the other dot is a C in the picture.
Here?
Yeah.
No. The dots, like 1 and 2, they refer to the 2 columns or 2 rows. So B acts inside this dot or inside that dot, and C connects the 2 dots. So now, out of this template, we've made something like a Majorana chain. And notice this alternating term. It's actually A times identity C minus IA, and so on. Oh, I guess it's, sorry, it's the other way around. Just a second. See, it's my. Anyway, let's forget about the sign. I'm not sure how to translate this metrics formula to a picture, but there is some difference. And if this matrix is gapped, one can show that the new chain is gapped. And to show that the new chain is gapped, one needs to do the Fourier transform, like I did for the Majorana chain. And you just study the spectrum for all Q and show that for all Q's, the spectrum is gapped, and therefore it has a ball gap. And of course, you need a general property that the definition of the ball gap I gave is consistent with the Fourier transform definition of a gap if the system is periodic. My definition is more general. It applies to non-periodic systems. So,
can you explain the dimensions there? It seems like you have every vertex is connected to 3 other vertices instead of 1. There's like 4.
this vertex is connected to itself with an anti-symmetric matrix B. And with the Majorana chain, we didn't do that because there was only one site, one Majorana on each dot. To make an anti-symmetric matrix, you need at least 2 Majoranas inside that little circle.
He says about C,
Oh, C.
because there is 3 entries.
Yeah, as I say, these coefficients alternate. Okay, let's look at this coefficient. Let's call it H. And this will be called J. And they will alternate. H picks up a C from here and A from there. So H equals C plus I tensor identity. And J, it's this term minus C plus V identity.
What's the little n?
Little a is this coefficient. It's a coefficient in front of the identity. It's an arbitrary number. Yeah, you can take it to be 1. Without it, there would be no gap. And it would be a critical Majorana chain. It will have J equal to C roughly.
H negative.
You can take it negative, yeah. So I claim that you could you get an energy gap in this case, and I also need to define nu, the second operation, and this nu is actually a textbook K-theory operation. You can look it up in Karubi's book. So let me define nu. We have L n plus 1 e minus 1 q. And this is the same as L T Q plus 1 n plus 1. Because if we have a matrix with some number of positive and some number of negative Clifford generators, we can double it like and the new matrix anti-commutes with sorry. This is positive and that is negative. So this is for free. Now, we have some metrics A tilde here. And the Clifford generator E2, which is negative. Out of this two matrices, we can construct another matrix that depends on the parameter. And let me write a formula like A double tilde of T equals like a sine pi over 2T times E2 this two matrices anti-commute, and that guarantees the conservation of the gap. So we have a well-defined family of matrices, and for T equals 0, equals 0, only this term remains. The matrix is E2, and for T equals 1, the matrix is minus E2. E2 is not the special point. We should make a slight modification of this path. We should go from our preferred base point to E2, and at the end we need to go back. But that is just a technical detail. Basically, we have a path between E2 and minus E2 that is defined by A tilde, and eventually it depends on A. And E2 is no longer a symmetry. This matrix in general does not anti-commute with E2. But E1 is still a symmetry. So we have recovered our P, and A tilde A double tilde belongs to omega of L n plus 1 E Q PQ. And as I say, this is a standard construction from K-theory. It defines an isomorphism. But perhaps the standard proof is not applicable to local matrices. We have to prove it again. And actually, one can use this diagram to prove things. Let me just make some claims. I claim that the composition of two maps is homotopy equivalent to alpha. I'll not show it. It will take some time to prove that. What I want to show is that the composition of nu and beta, which takes us back from the n plus 1 dimensional world to the n dimensional world, has a very simple picture. And that picture can be used to algorithmically construct invariant of high dimensional systems. They're reduced to invariants of zero dimensional system, and those are just linear algebra problems. So beta composed with nu has this simple picture. We have a one-dimensional system, or n plus 1 dimensional system that depends on parameter. It doesn't depend on a parameter yet. It has this Clifford generators. We're adding a positive Clifford generator, and we're applying beta. So let me show you how it works for p equals 1, q equals 0, and n equals 0. Those numbers are zeros, and let me take an instance of such metrics, and this will be the Majorana chain. And continue. By this construction, we double the Majorana chain. So there was a Majorana chain with coupling J. We double it. And we get the Majorana chain with negative couplings. E2 is a coupling between these sides. And E2 depends on parameter t that varies from 0 to 1. But now we're applying this map beta that changes time into space. And the parameter will vary from the left hand to the right hand. It means that here we're coupling the ends of the Majorana chain with strands 1. And on the right end, we're coupling them with strands -1. And in the middle, we leave those chains free. And we should allow sufficient region in the middle, given by that R in the locality level, which should be greater than the little r by some factor like 10. I don't know. One needs an estimate to actually run this algorithm. So we have produced a zero-dimensional matrix because we can consider all the sides as belonging to one big side. And that matrix has an additional positive Clifford generator. And that positive Clifford generator is just a flip about the horizontal line. So we have produced an anti-symmetric matrix A with a positive Clifford generator. And such according to this formula, and we know what that is. These are symmetric matrices with one positive Clifford symmetry, which are equivalent to orthogonal matrices. And for orthogonal matrices, there is an invariant, which is the determinant. So essentially, we are extracting an orthogonal matrix from here. And then we calculate the determinant. And in general, this matrix does not square to 1, but the sign of the determinant will be a topological invariant. So this is an algorithm. We take two copies of the a chain. We don't know whether it's the Majorana chain or something else. We glue like this, and we calculate the determinant. And that works with some modifications for all 8 cases of the Watt periodicity. Okay. Now let me move on to something that I don't know. So far I have been lecturing about things that I understand. Now I'll say something about things that I don't understand, trying to understand.
Yeah. Question then, when you use the determinant in one of the other cases, you need a super determinant or they don't?
No, just the determinant.
Only a bit.
Yeah, sometimes you need a Pfaffian.
Oh.
Yeah, it depends on where you are on the clock with a tick.
In other words, the Pfaffian and the determinant gives you eight possibilities.
There are also 2 cases, like in some cases the dimensionality, the invariant is dimensionality, like over real subspace. You have a projector acting in a real space, and the dimensionality of the space on which it projects may be an invariant. And there is yet another case where the space is quaternionic, and similarly, you should consider the dimensionality of quaternions. There are 2 Z's and 2 Z2s. Okay. Yeah.
One question. So how did you arrive at this L with Clifford symmetry? Can you prove that for any matrix, a anti-symmetric locally count before that maybe one of the
No. I am considering a more general question, and I should adapt the previous definitions to this setting. The Clifford symmetries act locally on each side, and each side previously had an elementary block 2 by 2, like 0, 1, 1, minus 1, 0, and now it has to have bigger elementary blocks. We have local anti-symmetric matrices without Clifford symmetries in n dimensions. They're mapped to or contained in interacting invertible systems of fermions in n dimension. And this is contained in topological systems in n dimension. That is contained in gap systems in n dimension. And I'll try to actually define these two things at the end of the lecture, and maybe say a bit about that thing. Let's take a temporary definition of Fn. This definition is, like I said previously, we take a system and some complementary system, and we can continuously deform this double system into a trivial system without something breaking down, like without closing the gap. And I'll specify what should remain. But even not specifying what should we wait on this path, we can give an alternative definition that turns out to be equivalent. There is a local quantum circuit that takes the product state, like 0. And there is a local quantum circuit U, which now we should discard the boundary or margin. And we get rho tensor rho complementary. Rho is our quantum system, and complementary is some other quantum system. And the condition is that it factors into two independent systems. One of them is the system of interest. And this condition may be defined up to approximate equality up to epsilon in the trace norm. Okay, now let's talk about properties of such systems that we think we know. I'll be very careful. I'll not make wild conjectures. So we have n, a parameter n, and I'll list pi minus n of LA, the spectrum LA, if A is any spectrum. Then pi minus A of E is the same as pi so pi minus n means pi 0 of LA sub n, which means different phases. Phases are connected components over space. So we're classifying faces in dimension n. And in the first column, I'll write something that follows from what we already know, namely LA n is the same as KO, a member of the KO spectrum in dimension Kn minus 2. Or I'll put it this way, LA equals KO shifted by minus 2. Or shift by minus 2 is like sigma minus 2, or omega 2. So this is the Bott periodicity picture in dimensions minus 2, minus 1, 0, 1, and 2. And I'll not go further. I could go further, but let me just stop here. There is something that is given by Bott periodicity, and Z 0, Z2, Z2, Z. And this is the fundamental Z2 of the KO spectrum. Like the zeroth member is Z times BO.
Do you mean to have negative n there and negative 2, negative? Yeah, okay, all right.
Did I do something wrong?
I think it's good. No, I'm.
The Z2 for the n equals 0 can understand is just a fermion even, fermion odd state.
Yeah.
And this for the 1 will be the Majorana chain, and the for the Z for the 2 like this Chiral charge here.
Yeah, yeah.
The quantum odds.
So the generator here is the Majorana chain. Sorry, in dimension 1.
Yeah, that's right.
Majorana chain. The generator here is called P plus IP superconductor.
Yeah,
And the generator here is a fermion, something with odd fermionic parity. And the generator here is the Berry curvature. But I'm actually talking about maps to pi minus n to Fn. There should be maps in this direction. And in dimension minus 2, this is an equality. So it's Z, it's an isomorphism. Z2, Z2. And here I put a question mark. But anyway, there is such a map that maps the generator P plus IP superconductor to the same phase interpreted in terms of interacting fermions. And potentially it could be a trivial phase, because we know that this is non-trivial if we restrict ourselves to quadratic Hamiltonians. But if we allow higher order terms in the fermions, it could be connected by paths to the trivial phase. Actually, it is not. But this map is injective. And let me also write a similar thing for bosons, because for interacting systems, we can also consider interacting spins. And if those systems do not contain fermions at all, they will have a different classification. B So we have maps in this direction and maps in in that direction. Bosonic systems are mapped to fermionic systems. And Z0, 0 question mark. But we also know some non-trivial bosonic phase that maps injectively into this question mark, and that is the E8. It's some two-dimensional system which has an E8 chiral CFT at the boundary.
Another zero.
Oh, yeah. -1, 0, 1. Yeah, it should be. Right. Now, let me call this map U, that map V, and we have an interesting identity. U of P plus IP equals V, not exactly, you'll see, of E8. Actually, 16 copies. Of this equals V of E8. And this system has chiral central charge 1/2, and that system has chiral central charge 8.
B is a map to tile map. Tile.
V is a map from, well, let me write it, Z times E8. Phi and the generator of this Z is called E8, and the generator of that Z is called P plus IP. Pi minus 2, yeah, pi minus 2.
It suggests that this bosonic system is built from the lattice E8. Diagram E8.
Yeah, but it's the edge that has E8. The bulk that doesn't know about E. At least I don't see how E8 comes up in the bulk. There is a model that produces an E8 CFT on the boundary. And as I say, this maps are injective. This is something we can show, although not completely rigorously. But I'm not completely sure that they're surjective. There might be some phases that we don't know at all, and they're not described by known topological invariants. That is still a possibility. Now, even if we didn't know those things, these things are known by examples, and the injectivity requires some subtle arguments that are not completely rigorous at the moment. But even if we didn't know anything about that, we could still make some statement. Namely, we know that F2 equals Cp infinity cross Z2, and B2 equals just Cp infinity. And this is very easy to, zero. This is very easy to understand. In zero dimensions, we have just Hilbert spaces and states in those Hilbert spaces. And this is a space of pure states in the Hilbert space, sufficiently large dimension. And that is equivalent to KZ2, which allows us to construct certain maps. Namely, let me just write it down. First, we can construct K Z n+1 map to Bn. I'm considering bosonic systems for simplicity. This also applies to fermionic systems. And collectively, those maps can be regarded as a map from the Edinburgh-MacLean spectrum shifted by 2 to the spectrum B. And
Shifted by 2.
Oh, 2, yeah, just 2. Thank you. In particular, we can apply this map to a classifying space of a compact group. Suppose that G is a compactly group. Then we have a map from H n+1 n+2 of BG to maps from BG to Bn. And such maps describe SPT phases, symmetry protected phases, symmetry protected topological phases. So given an element of this cohomology group, we can produce a symmetry protected phase. And that was first done by Chen, Guo, Liu, and Shagan Wen. And did I list all the authors? Okay, good. So they make this map very concrete. They constructed concrete SPT models. But one can argue abstractly that since such a map exists on the level of homotopy theory, such models should exist. And this goes in this direction. It basically uses a map from Z to pi2 of B. And we can go in the other direction. To go in the other direction, we need to start with the following. We can consider a map from pi n of X. X is an arbitrary space. to Hom of Bm of X, Bm of Sn. And this is a very simple map because an element of pi n of x is some map f from Sn to x. And we apply the cohomology functor to that map. And one can also formulate this map in a different way. We can consider a map between the product of this and that into this target. And we can swap the two factors, and this way we get something like.
Alexei, question. So Hom in which category?
Excuse me?
This Hom is in which category?
Oh, Hom in the category of abelian group.
Okay. Thanks.
Mm-hmm. Bm of X and is mapped to Hom and that thing is known. It's just pi m n minus f of b, and we if we take n equal to m plus 2, this is z. So let me just do that. Let me just use m plus 2 z. Okay, good. We have constructed a map from Bm of X to this Hom group, Hom set. And we can also map it to Hom let me use R. Mike used C cross, but I'll use R. And we can continue to I should say that this is an important equality. That Hom set, Hom group is isomorphic to the real cohomologies.
And then let's say
It's not true.
like the two torus when m is 0 has a
Excuse me?
when m is 0, the two torus has an H2 but not a pi 2.
Yeah, I agree. I forgot to, I skipped one step. This sequence of maps is compatible with suspension. And in the end, we get stable homotopy groups. Is it okay now? Uh, yeah, so it's actually stable here.
And it's,
Any problem? Good, good. So now there is something that I don't completely understand, as I say, the existence of a map of the composed map, which vanishes if we compose it with a map from R to R divided by Z, means that there is a lift to a map to IZ. So on very general grounds, we have argued that there is a map from Pm of X to from B to IZ shifted by 2. And that is a completely abstract argument. It only uses the fact that Kzn plus 2 agrees with B for n equal to minus 2. That's all. But we can give a physical interpretation to that, particularly to this map. If we have Bm of X, these are just maps from X to bosonic faces in dimension M. So we have a parametrized family of bosonic systems in dimension M. And one can define so-called Hilbert curvatures on bosonic faces. They described by Kapustin and Spodeneyka, their paper. And this map is actually induced by Hilbert curvatures. So that is a physical map. And that physical map corresponds to that abstract map. And it also corresponds to a chiral central charge. A chiral central charge is something that is not guaranteed to be defined for all faces. We believe it is defined for all faces, and we believe that these are equivalents. But let me describe the chiral central charge. Chiral central charge yeah, what is this? The chiral central charge is some quantity that corresponds to energy current. Suppose we have a system with an energy gap in the bulk, and we consider the boundary at temperature T, and there will be an energy flow along the boundary equal to energy flow Energy flow is well defined for phases that we know, in particular for P plus IP and the E8 theory. It might not be defined in general because there is a problem. We need local correlation along the boundary, and it's conceivable that such correlations just don't exist. We don't have a complete proof yet. Everybody thinks that they exist. And if they exist, then the maps that are shown are one-to-one. This U and V are just isomorphisms. But in general, one can say that if we apply this map to some phase that has a chiral central charge, then it gives two times the chiral central charge. The value of this map on the phase for which this energy flow is defined is 2c minus. And in particular, it shows that C minus is well defined for modular 12, and Nikita Sapenka proved that C minus is actually well defined modular 24. Yeah, so basically that's it. I think I'll not discuss it the analytic detail.
We're running late. Yeah, good question.
Sorry, so do you think it's possible to define some sort of differential refinement of this when equal conditions? Like some secondary characteristic classes.
Like what?
Well, like, I mean, like, don't you have differential topologies, right? Can we do the same thing for this equal topology?
I don't know.
This, we got, we lost you. This chiral chart is an integer.
No.
Oh,
So
just in some.
and
It's best defined though in -2, in pi -2.
yeah.
Okay. Okay.
Mhm.
That right.
Yeah, so
the central charge is this chiral charge is an integer, right? Yeah. 2 times C minus.
yeah, it is an integer for invertible phases. For non-invertible, it's not true. But to make this more clear, it's 0/24. And 2 times the chiral central charge is an integer, but it's mapped to an element modulo 24. And therefore, C modulo 12 is well defined according to this argument. And according to Nikita Sapenka, it's actually well defined modulo 24. And we all believe it's well defined as a rational number, but nobody has proven that.
So, well, let's thank Alexei and all. And again, if you want to access the building over the weekend, there are key cards available. And we'll see hopefully most of you Monday morning, 8 o'clock.
So maybe you're in the morning and definitely will be. If you have any suggestions, send it by email.
Work done in the like the UG in the paper we just
When are we doing this? Right away? No. I saw my chance to go to the swim back.
I think I'll go.
Still go right away?
Extreme.
Oh, yeah, that's not close.
But I mean, if you come along, if you are there later, because it will be open.
I will be there later.
Yeah, so it's just message you.
You're not done. Taking your mic. Sure.
Well, I don't know. I mean, so, I mean, I'll.
That's perfect. I don't like. Yeah, I mean, the practice has been very intensive. I might come to regret.
Number.
I'll do that. Yeah, well, I think that I also think I went place. Now, if I other people who are running the I8s and reversing the things that way, so I see the like. People who are doing the modeling. I didn't think that like say. Yeah. Anything with these assumptions, so I. I don't know. You know, that's like, yeah. Austria. Is that after there's and so when is everybody trying to last day? Like they look at I don't think that's like that. It's just on the other side of the border, but they were like neighboring towns. It's just that now they're by the neighboring was familiar. I didn't know I named Shapiro and there's like it's called oh yeah, and Shapiro I didn't know that. Yeah, back to the, I mean, why were they on the right? Because the Romans ruled the right. Yeah. And then they were invited by the This is also bad. Right. But one was there was so Russia conquered right. Well, the Commonwealth of Poland and was one of the main powers in Europe. Yeah. Yeah, it reached most of Ukraine, most of southern Ukraine has been populated.
Yeah.
Because the border between Slavikos and but insofar as it was part of Europe, it was part of partial matrix before the second. Where essentially the subs are being coded from either way.
Oh, wow. Yeah, okay. And, but I mean, there was,
No, the Russian never coded. Good,
no, I didn't say
good
it's
with
bad.
bad by Russia.
Oh, wow.
Yeah, even after the conquest, this was called the Pale of Settlement, and Jews were not permissible to move outside of the
Okay, that I didn't know. I mean,
Yeah.
that is,
It gets pretty interesting. Have you heard of Karaite?
what is it?
Karaite.
Alright,
It
so,
turns out that there are two kinds of Jews. There's the rabbinic Jews. We don't know exactly when they are. In Hebrew, it's Karaite. So they're Jewish, but they follow a completely different traditions of Jewish laws. So I don't know.
one doesn't understand, but that's a bias.
So for example, rabbinic Jews,
Sure.
the most important religion is rabbinic Jews will not like. But they will, they're happy. They've been lit.
It's been lit by a.
Already been. Before Shabbat. Karaites refuse to even have lights that have been lit before Shabbat, during Shabbat.
Was that?
They live in the dark.
Different interpretation.
Any post-Mosaic interpretation was valid. That you had to simply stick to the text. There's a great
So that's amazing. Religious scripture.
There were two rabbis having a dispute. They were disputing the correct interpretation. So one of them summoned an angel who said, "You are right," and it was ruled that that was invalid. That's not evident.
But one of the main things that is fascinating is like this, something that kind of that is with regards to this Jewish scripture and like how to this day there are so many nuances kind of that are still being debated. I mean, that with the Israelite transformers,
That's rabbinic Judaism.
yeah.
The Karaites have a different. Anyway, why did so the Karaites. We don't know exactly. It would be, as far as I know, 500,000. Most Jews live in Mesopotamia. The problem is the Mongols live.
They came
Destroying this.
Yeah.
The world mathematically after that, but back then was the largest in the world. The Jewish community was centered in the city.
Yeah.
Because they're also the most important cities for Shiites. Yeah. So yes, that sounds like but we don't know exactly like the disagree with that. So the Karaites also had a population of Crimea and even maybe lively in, I think because it had been under Tatar rule, and so they had under maybe there were migration